Today we're going to talk about directional derivatives and gradients. So in this particular section, we are finally going to be able to do what we've been talking about in class a lot, which is finding a derivative in any direction. We'll have particular directions that we're calculating derivatives in, but the idea is that before we were finding derivatives at some point and it was like in the positive x direction or it was in the positive y direction. So those were the first partials, f sub x and f sub y. But the question that kept coming up was, what if we want to take a derivative that doesn't point in those directions? How do we find it? And so it turns out it's actually not that hard. All we need is a unit vector. And that unit vector needs to point in the direction that we're interested in, okay? And the reason that it needs to be a unit vector is so that its magnitude doesn't inflate the value of the derivative, all right? So we're going to have a unit vector, and then we're going to have our partial derivatives, f sub x and f sub y, and we're going to calculate this thing, and this thing is called the directional derivative of f in the direction of u. And the notation is right here, this big D sub u of f of xy. That literally means directional derivative of f in the direction of u. And what this gives us is the slope of a tangent line. And it is in the direction of u, the vector, the unit vector that we have. And what we do is we take the first partial with respect to x, and we multiply it by the first component of the unit vector. Then we take the first partial with respect to y and multiply it with the second component of the unit vector. Then we add them all together. And together, when we add those, it's going to give us just one number. Well, I shouldn't say one number because it could be something like -2 minus the square root of 3. Still one number, but it's not a function if we're evaluating it at a point. And so what it's going to give us is the slope of the tangent line in the direction of u. And so we can look at this in a picture. So in this picture, for example, I've got a point P, and like we're on a hill here. And let's say that we're standing on a hill at this point P on this surface, and the intersection of this point with a vertical plane that runs parallel to the z-axis creates this sort of curve, this curve C, okay? And on this curve C, let's say we're facing in the direction of this curve, there's another point Q. So we are standing on P, looking towards Q, and wanting to figure out what is the slope of the tangent line right at the point. Like if I'm standing at that point P and I'm about to take my next step in the direction of Q, what is my slope? Will it be negative? Will I be going downhill? Will it be positive? Will I be going uphill? Will it be 0, which means there is no hill? What's it going to be? And so in order to do this, what we have to get is a unit vector, and the unit vector is down here on the xy plane. Here's my unit vector. And my unit vector is parallel, so we've got the unit vector u is parallel to the directed line segment PQ. So if I'm standing at P, aiming towards Q, and I want to get my derivative in that direction, then I just need a unit vector that runs parallel to that, okay? And then in that case, let's see, I think I've mentioned everything here. T is the tangent line at P. Okay, so once we get that U vector and we have our first partials, this T, this red line that's up here, that's the tangent line at the point P. And so it has the same slope as as what we're calculating. In other words, if we were to get our slope in that direction, we could also come up with the equation of the tangent line to that curve C where that point is intersecting. Okay, now if U, our unit vector, makes an angle with the x-axis, then we're going to have to write our unit vector using trig functions. And what we'll use is u equals cosine theta, sine theta. And the reason that that works is, we can kind of see it here in this graph. In this graph, if I have theta as being the value of the angle that my unit vector makes with the x-axis, then taking cosine of theta would give me my adjacent, my a, over 1. Okay, so that's going to give me my a value for my unit vector. And then sine of my theta will give me the opposite, b over 1. Okay, and now if I was to take the magnitude, so these are going to be my two components. Remember, up above we had the unit vector has components a and b. If I was to take the magnitude now of some vector ab, what I'm looking at doing is actually saying, well, a is actually equal to cosine, and b is equal to sine. And I'm going to take the magnitude of that instead. And the magnitude says we take the square root of the sum of squares of the components inside of the vector. And so that means we're looking at the square root of cosine squared plus sine squared. And our Pythagorean identity says this is just the square root of 1, which is 1. And so that's why cosine and sine of the angle work as a unit vector, because their magnitude will give us 1. Okay, so we're going to have different scenarios. Sometimes we'll be given a unit vector and we just use it. Sometimes we will be given a vector and it won't be a unit vector, so we make it into a unit vector by dividing out the magnitude. And then sometimes we'll just be given the angle that our unit vector, based on the direction that it's pointing in, there's an angle between it and the positive x-axis that we will use to help us derive what cosine of theta and sine of theta are. Okay, let's look at an example. In this particular example, we are going to be finding the directional derivative for f of xy equals 9 minus x squared minus y squared. First of all, this shape right here is an upside down circular paraboloid. So it's like a big hill, okay? And we want to find the directional derivative at the point 2, 2. Now, up above, we were told that the directional derivative in the direction of u of f of xy can be found by calculating the first partial with respect to x of xy times a plus the first partial with respect to y of xy times b, okay, where a and b are the components of my unit vector. Now remember, from chapter 12, we use the letter u to indicate a unit vector. So if we're not using u, then definitely don't assume that it's a unit vector. Just assume that you're going to need to fix it and make it a unit vector. Okay, so given this formula, if I want to find the directional derivative in the direction of u equals negative 1 over root 2 with negative 1 over root 2, that means I need to find my first partials first. Okay, I need f sub x, I need f sub y, and then I need to evaluate them at the point that we're working with. Because now if I go through here and I replace, so I got the directional derivative in the direction of u of f of 2, 2. That's going to be f sub x of 2, 2, and times a plus f sub y of 2, 2 times b. And this should give me a number when I'm done. Okay, let's find our partial derivatives. F sub x of xy, if I look at my f of xy, it's equal to 9 minus x squared minus y squared. If I take a partial derivative of that with respect to x, the 9 and the y squared are both constants, so they go away. And I just end up taking the derivative of minus x squared to get negative 2x. Now I need to evaluate that at 2, 2. And that's going to give me negative 2 times 2, which is negative 4. All right, f sub y of xy is equal to, now I run a del y through my function. 9 goes to 0, x squared goes to 0, and I'm left with minus 2y. And then I'm going to evaluate my f sub y at 2, 2. It gives me negative 2 times 2, which is negative 4. Okay, those are the values that I need. So now in part A, using my form up here, right, so this is my little formula that's going to help me. The directional derivative in the direction of u of f of 2, 2 is equal to negative 4 times a, and a is a negative 1 over the square root of 2, plus f sub y of 2, 2, so that's negative 4, times b, which is negative 1 over the square root of 2. This leaves me with 4 over root 2 plus 4 over root 2, or in other words, 8 over the square root of 2. I can rationalize that if I want, although it is not necessary. We can just leave our answer this way. What this is saying, this 8 over square root 2, is this is the slope at the point 2, 2 in the direction of negative 1 over root 2 with negative 1 over root 2. So you're like standing in the hillside at the point 2, 2, and you look in the direction of negative 1 over root 2, negative 1 over root 2, and the slope is positive. That means you'd be going uphill. Okay, that's all that means. Part B, we're still calculating a directional derivative, but now it's just a different unit vector. That's all. That's the only difference here. Here they're telling us that u makes an angle of pi thirds with the x-axis, so I need to get my direction. That means that u is equal to a vector with components cosine of pi thirds and sine of pi thirds, because all they gave me was the angle. They didn't tell me the numbers that go in my unit vector. And I can calculate these. Cosine of pi thirds, that's going to give me a 1/2. And sine of pi thirds is root 3 over 2. Okay, that's my unit vector. And so now when I calculate the directional derivative in the direction of u of f of 2, 2, the only thing that's changing are my a and b values. I'm still using f sub x of 2, 2, okay? So that's a negative 4, and then times a, which is 1/2, plus f sub y of 2, 2, which was negative 4, times b, which is root 3 over 2. And when I multiply everything through and simplify, this becomes negative 2 minus 2 root 3, okay? And so then this is the slope at the point 2, 2 in the direction of 1/2 square root 3 over 2. And this slope is negative, which means you would head downhill. Okay, so that's two different ways to calculate a directional derivative, where the two ways are just have to do with the different ways that we come up with the unit vector. Like I said, sometimes it's given to us, like in part A, and sometimes we have to make it, like in part B, where they just give us an angle. Okay, the next topic is the gradient vector. So one of the things that we saw with a directional derivative is that it is f sub x times a plus f sub y times b, which looks like the result of a dot product. And the dot product I'm talking about is a dot product where the first vector has the first partials, f sub x and f sub y, and the second vector has components a and b. Now, we've got some new notation we're being introduced to here. It's called the gradient vector. And that is this guy right here. I want to talk about this just real briefly, okay? This upside down triangle with a hat on it The hat means it is a vector. It is called the del operator, and that's capital D del operator. And it operates on things. In particular, if we have del f, that is a scalar multiplication, where f is the scalar and del is the vector. What the del vector is a vector with components del x, del y, and del z. So it is a vector with all of the first derivative operators, and it will act upon a scalar function f of x, y, z, for example. I'm using 3 variables just because that covers our bases. So if this del operator comes along and operates upon some scalar function f, what happens is you would distribute the f to each of the components inside and then let the actions take place. What those actions will be is our actual first partials. So in the first component, when the f hops in with del x, we suddenly have del f del x, which is the first derivative of f with respect to x. We also have del f del y and del f del z. Okay? For short, we write the del f, and it's understood whenever you see del f, you are looking at the gradient vector. Okay, this is our gradient vector. And the gradient vector is just the vector that has the first partial derivatives of a function. Okay? If we take that gradient vector and we put it in a dot product with a unit vector, that is going to calculate the directional derivative. So that's the relationship between the two. We already saw this part in the last little section. The directional derivative of f in the direction of u is f sub xa plus f sub yb. Now we're just seeing the pieces that are put together to make this. So it's the gradient vector that's new, and we have to know it. So when you see this notation, make sure you know this, okay? We are going to see the del operator in the future in chapter 16, and we're going to see it do different sorts of operations. So we want to be comfortable with the gradient vector and what's happening with the del operator in the gradient vector so that we're comfortable with the further operations that we see. Okay, and so this definition will extend to higher dimensions, of course. Now, we had a long time ago, way back in 12.3, I want to say, we were told that a dot product of two vectors, A and B, is equal to the magnitude of A times the magnitude of B times cosine of the angle between them, right? Now, if a dot product is equal to that and a directional derivative is a dot product, then technically we should be able to say that the directional derivative here of f in the direction of u is just equal to the magnitude of the del operator, the gradient vector, times the magnitude of the unit vector. Wait, the magnitude of a unit vector is just 1. Okay, so that's going to go away in the next step. Times cosine of the angle in between them. Okay, we'll come back to this and where, like, the one place where we're actually going to use that and the implications of it. In practice, we don't really see it too much in any of our homework problems. It's more about what the different angles can give us that is going to be important for us. Okay, so let's see. You have to have a gradient in order to calculate a directional derivative. All right, so we're going to calculate a few more directional derivatives, but now just using this idea of the gradient vector. So we're not doing anything new. This is absolutely 100% not new. It's just looking at it differently. So in this example, we're told to find the directional derivative of f, which is equal to x squared y cubed minus 4y at the point 2, -1 in the direction of 2, 5. So this is what we're being asked to find. Directional derivative in the direction of u of f of 2, -1. I'm just going to write this. It's equal to question mark. Question mark is what we are trying to find. So what we need is we need our gradient vector evaluated at 2, -1, and we need a unit vector. Okay, so this is the gradient, and then this is the unit vector. Okay, so in order to get the gradient vector evaluated at a point, we need to first calculate the gradient vector. So let's do that. The gradient vector f of xy is equal to, well, in the first, I'm gonna write out all the gory details here. So in the first component, it's del x of x squared y cubed minus 4y. The second component is del y of x squared y cubed minus 4y. So I go ahead and take those derivatives. The first component becomes just 2xy cubed. The second component becomes 3x squared y squared minus 4. Okay, that's it. That's my gradient vector as a function. Now we have a specific point that we want to evaluate this at. So we'll calculate del f of 2, negative 1. Everywhere there's an x, put in 2. Everywhere there's a y, put in negative 1. This gives us 2 times negative 1 cubed, comma 3 times 2 squared times negative 1 squared minus 4. And this finally simplifies to be, it looks like, negative 4 in the first component. And then we get 3 times 4 is 12 minus 4. That's going to be 8 in the second component. Okay, that is our gradient vector at the point 2, negative 1 for this surface. So we have our gradient. Now we need the unit vector. All right, so our unit vector will be equal to the vector that we're given, 2, 5, divide out the magnitude of that vector. And the magnitude is going to be the square root of the sum of squares, so 2 squared plus 5 squared, which adds up to 29. And so this simplifies to be 1 over the square root of 29 times the vector 2, 5. That is a unit vector. Okay, I think we have all the parts that we need. So we can now calculate our directional derivative in the direction of u of f of 2, negative 1 is going to equal, I'm just going to write it out, the gradient of f of 2, negative 1 dotted with u. Okay, now we'll put those pieces in. This becomes negative 4, comma 8. That's my gradient vector, dotted with 1 over the square root of 29 times 2, 5, the vector 2, 5. Now that constant that's in there, I can pull that out to the front. So this becomes 1 over the square root of 29 times, in parentheses, I'll do my dot product, negative 4 times 2 plus 8 times 5. That becomes negative 8 plus 40, or 32 over the square root of 29. So if I had not made my vector into a unit vector, then that square root of 29 in my denominator would not be there. I would only have the 32, and I would think that my slope value is 32, when in fact it's 32 over the square root of 29, which is a much smaller number. So the unit vector, if it's not a unit vector, is going to cause problems because it's going to inflate the value of the slope. Always divide out the magnitude. Okay, even if you just need it to do it to be safe, you're not sure it's a unit vector or whatever, just go ahead and calculate the magnitude, divide it out. All right, I am going to now we're going to move on to maximizing the directional derivative. To maximize the directional derivative, we have to talk about a few things here. So if we have a function f of 2 or 3 variables at some point, here's some things that we should know about the directional derivative. Now, before I even state what those are, I want us to recall from the previous section where I said that the directional derivative in the direction of u of f of x, y can also be represented as just the magnitude of the gradient vector times cosine of the theta. Okay, where the theta is the angle between the gradient vector and the unit vector. Now, let's go to our 3 things. The maximum value like the biggest value that you'll get of a directional derivative at a point is just the magnitude of the gradient vector. That's it. This happens when u has the same direction as the gradient vector. Okay, let's think about that. If u and the gradient vector have the exact same direction, that means they're parallel. And that also means that the value of theta between them is 0. Okay, so then the directional derivative would just be the magnitude of the gradient vector cosine times cosine of 0, which is 1. So I'm going to keep coming back to this recall function up here. The next thing to know is that the minimum value, like the smallest value you could possibly calculate for a directional derivative of a surface at a point, is the negative of the magnitude. And this occurs when the unit vector has the opposite direction as the gradient vector. And if a unit vector is pointing in the opposite direction of a gradient vector, that means that the angle between them, theta, is equal to pi. So if we think about going back up here to this directional derivative being equal to the magnitude of the gradient vector times cosine of theta, cosine of pi is -1, and that's where we get that negative sign in front here. Okay. The next one is when u, the unit vector, is orthogonal. Remember, orthogonal just means perpendicular. So when u is perpendicular to the gradient vector, we have to think, what's the angle between the two? Well, if they're perpendicular, the angle between them is pi halves. And if theta is pi halves, let's go back up to our little recall function, cosine of pi halves is 0. And so the directional derivative would be 0. So if we calculate a directional derivative and we get back 0, then we know that the unit vector was normal or perpendicular to the gradient vector. Okay, so those are 3 things to know. All right, in this next problem, we're going to really get our practice with calculating directional derivatives, and then we're going to talk about the maximum rates of change and such. But the reason I'm doing another directional derivative is because it is the last, or one of the last cases for the unit vector. We have done a problem where the unit vector was actually a unit vector. We have done a problem where we had to come up with the unit vector using cosine and sine. We have done a problem where we had to make a unit vector because all we were given was a non-unit vector. And now we're given 2 points, and we're going to have to come up with a unit vector. Okay, so I'm going to call these part A and B and work through them. In part A, we're told if f of xy is equal to x e to the y, find the rate of change of f at the point 2, 0 in the direction p to q, where q has the values 1/2 and 2. So this find the rate of change of f at the point and in a direction, that means find the directional derivative in the direction of u of f at the point 2, 0. So that's what we want to find, okay? But first, we need our gradient vector. Our gradient vector, remember, is just going to be the vector that has our first partial derivatives in it. So we've got del x of x e to the y in the first component, and del y of x e to the y in the second component. Del x of x e to the y is just e to the y. Del y of x e to the y is x e to the y. Okay, now we need that gradient vector evaluated at the point 2, 0. And so that means we're going to plug in everywhere there's an x, we'll put in 2, and everywhere there's a y, we'll put in 0. This gives us e to the 0, 2e to the 0, which simplifies to be 1, 2. So that's our gradient vector at the point. Now we need our unit vector, or direction. So it's not just a direction, it's also the unit vector that points in that direction. Okay, so we're given 2 points, and our unit vector should be equal to the directed line segment PQ, and then divide out the magnitude of the directed line segment PQ. Okay? So in order to create the directed line segment PQ, we take the values in Q and subtract the values in P from it. So here's what that looks like. All right, so the x component in Q is 1/2 minus the x component in P, which is 2. The y component in Q is 2 minus the y component in P, which is 0. I am going to simplify those first before I start calculating my magnitudes. Okay, 1/2 minus 2 is a -3/2, and 2 minus 0 is 2. All right, so my magnitude is the square root of the sum of squares, so 9/4 plus 4. 9/4 plus 4 is equal to 25/4. So I have the square root of 25 over 4, and the square root of that is just 5/2. So this is going to equal -3/2, 2 over 5/2. Rather than dividing by a fraction and leaving it that way, we should flip the fraction and multiply. So this becomes 2/5 times the fraction, or the vector, -3/2, 2. Okay, that is our unit vector. Okay, so we should be able to take this and dot product it with our gradient vector and come up with our directional derivative. So the directional derivative in the direction of u of f of 2, 0 is equal to the gradient vector at 2, 0 dotted with the unit vector. And so here's what we get. We have 1, 2 dotted with 2/5 times the vector -3/2, 2. Now, of course, the 2/5 can come out in front. So I'll pull that out in front. And then I'll do my dot product. 1 times a -3/2 plus 2 times 2. -3/2 plus 4. So we can rewrite 4 as 8/2. So this becomes 2/5, and then 8/2 minus 3/2 is 5/2. So this all simplifies down to 1. That's the value of our directional derivative in the direction of the point Q if we start at the point P that was given. Okay, that answers part A. Part B, we are asked, in what direction does F have a maximum rate of change? Okay. So we're told up above that the direction of max change is the gradient vector. And it's the gradient vector at this point 2, 0, because we're still talking about the same problem. Okay? And that value is a vector, and we already calculated it. It's the vector 1, 2. So that is the direction where we would find the greatest rate of change, or the maximum change. Okay, I guess I should write that. Instead of max change, I'll write max rate of change. Okay, the next question is, what is the maximum rate of change? Okay, so we found the direction. Now we want to know the max rate of change. It's got to be a number, not a vector, is the magnitude of the gradient vector at 2, 0. So that's going to be the square root of the sum of squares, or the square root of 1 plus 4, which is the square root of 5. That's the value of the maximum rate of change. Now, a side note on this, because we're done with our problem, we finished this. That second part, part B, was asking us for the maximum rate of change and the direction of the maximum rate of change. But a side note to put in here is the direction of the minimum rate of change is negative of the gradient of f of 2, 0, which just means a negative in front of that vector, 1, 2. That's it. There's literally no calculation needed. And then the minimum rate of change is the negative of the magnitude of f of 2, 0, which just means it's negative root 5. And that's it. So if you're asked a question about minimums or like steepest descent, that's another way to say that, then we're talking about the negative of the vector and the negative of its magnitude for the direction and the actual rate of change respectively. Okay? All right, next problem. We're still doing the same thing, but here we're going to focus on the actual just maximum rate of change of a function, f of x, y, z, which is equal to x ln of yz. We want to know what that maximum rate of change is at the point 1, 2, and 1/2, and the direction in which it occurs. You have to find the direction first. These problems always weird me out because they ask them in the reverse order that you would find them, which can lead people astray a bit. So the direction is the first thing that we can calculate. The direction of the max rate of change is the gradient vector of f evaluated at 1, 2, and 1/2. And then the value of the max rate of change is the magnitude of the gradient evaluated at 1, 2, and 1/2. So we need to find our gradient vector and then we can calculate these things. Okay, so our gradient vector is del f equals, all right, we're first going to find del x of x ln of yz, and then del y of x ln of yz, and then z, del z of x ln of yz. Okay, derivative with respect to x of x ln of yz. The ln of yz is a constant and the derivative of x is 1, so that first component just becomes the constant ln of yz. In the second one, x is a constant. The derivative of ln of yz with respect to y will be 1 over yz times the derivative of yz with respect to y, which gives me a z. Del z of x ln of yz, the x is a constant, and then the derivative of ln of yz is going to be 1 over yz times the derivative of yz with respect to y, which gives me, with respect to z, which gives me a y. Now I simplify these. In the second component, the z's divide out. In the third component, the y's divide out. And this leaves me with a vector with components, ln of yz, and then we get x over y, and then we get x over z. So that's our gradient vector as a function. Now we want the gradient vector evaluated at the point 1, 2, 1/2. So we're going to plug those values in for x, y, and z. Our vector ln of yz is ln of 2 times 1/2. X over y is 1 over 2. X over z is 1 over 1/2. Don't leave things like this because this simplifies a lot. 2 times 1/2 is 1, and ln of 1 is 0. The 1/2 stays as it is. 1 over 1/2 is 2. Okay, there's our gradient vector. This is the direction of the max rate of change. Okay, and then the value of the max rate of change is the magnitude of this gradient of 1, 2, 1/2, which will give us the square root of the sum of squares, so 0 squared plus a fourth plus 4. I can rewrite 4 as 16 over 4 and add those, And this gives me the square root of 17 over 4, or in other words, the square root of 17 over 2. That is the value of the max rate of change. Okay, so that's the gradient vector. That's how we use it to calculate the maximum rates of change and the directions in which they occur. Now, in the next topic, what we've got is this whole understanding the gradient vector physically. Like, what is this? Okay. So in this first picture, I have a drawing of a level curve. And remember, a level curve is when we have a three-dimensional surface and we let z equal some constant. And then we draw the two-dimensional curve on the xy plane and see what it looks like. The gradient vector will be perpendicular to the level curve, okay? And it will point in the direction of steepest descent. So that's what this picture is doing right here. So this right here is the direction of steepest descent. Let's see. Yeah, that's about it from there. Now, the steepest descent is when you travel in the direction of the gradient, which is orthogonal to each level curve. So that has to be true every time. So I really like this picture on the right. So if I start right here on this level curve, I have to leave the curve perpendicular to the curve, okay? So that I could form a right angle with my path and with the level curve. But then I need to aim towards the next level curve. And when I get to the next level curve, I need to get there orthogonally, right? So I have another right angle. Then I go through that curve, maintaining the perpendicular relationship and get to the next level curve. And again, still maintaining that there's a right angle there. When I go through that level curve and go to the next one, I have to turn a little bit to make sure that I get to the next level curve and I'm orthogonal to it. And similarly, when I move on to the next one, I have to kind of turn in order to maintain this right angle relationship between my path, my curve of steepest descent, and the level curves. Okay, so the steepest descent is when you travel in the direction of the gradient, which will always be orthogonal to the level curves. Depending on where you start, your path changes at each level curve. So if I had started somewhere else, my path would be different. It would look different. Okay. The gradient vector gives the direction of the fastest increase of f, since the directional vector is largest when the angle between the direction and the gradient vector is 0. So the gradient vector is perpendicular to the level curve, or if we go up a dimension, level surfaces of f through a point x naught, y naught, or x naught, y naught, z naught. Okay. Now, we can use the gradient as our normal vector for the equation of a tangent plane, so long as we're working with a function big F of x, y, z equals c. Now, we've seen a lot of planes in this class. In 12.3, we were just coming up with an equation of a plane. It didn't have a relationship to any surface. It was just the equation of a plane. Then in 14.4, was it 4? I think it was 14.4. We looked at finding tangent planes to a surface, and we came up with a few different formulas for that. And we were relating the tangent plane to the linearization function, or in other words, the linear approximation of a surface. Now we're going to kind of put the two together in the sense that we're going to use our gradient vector because it is a vector of first partial derivatives, which we learned in 14.4 give us the normal vector to the plane. Remember, plane always needs a normal vector. So plane needs two things. One is the normal vector, And fortunately for us, that's always going to equal the gradient vector. Okay, I'll do gradient of big F. Oh, needs two things. Sorry, that just erased. Okay, and then it needs a point. X naught, Y naught, Z naught. Okay, so if we have a big function, big F of x, y, z equals some constant, then we can go ahead and we can calculate the gradient vector. And we can dot it with x minus x naught, y minus y naught, z minus z naught, and set it equal to 0. After we do the dot product, here's our form. And it should look familiar. First partial with respect to x times x minus x naught. First partial with respect to y times y minus y naught. First partial with respect to z times z minus z naught equals 0. All those first partials are evaluated at the point in question, which is the x naught, y naught, z naught. Now, we have been working with f of x, y equals z. So maybe if you only want to have to remember one form for a plane, that would be a good idea. So if we're given f of x, y equals z, then we can just subtract z from both sides and define big F of x, y, z to equal little f of x, y minus z, and set that equal to 0. Then, when we calculate the first partials, the first partial of big F with respect to x will be little f with respect to x. First partial of big F with respect to y will be little f with respect to y. And the first partial with respect to z of big F will just be a -1. And then we can put those values in, and here's the form that we get. The only difference is right here where it's just a -1 hanging out. So that is our first partial with respect to z. Now, if I was to compare this with what we did before in 14.4 by distributing that negative sign and moving the z over to the right-hand side of the equal sign, these are the same. Okay, it just depends on how you define your function. So you take your pick. We have two different ways to find the equation for a tangent plane. You can memorize both of them or memorize this one, this latest one that we just found, and it will take care of all situations. So you need to know this. It is not on your formula sheet, okay? All right, now if we want to calculate a normal line to a surface at a point P, a normal line would be perpendicular to the surface. Now remember, the gradient vector is also perpendicular to the surface. And for a line, remember a line needs a parallel vector and a point. So if the line is perpendicular to the surface and the gradient vector is perpendicular to the surface, then we should be able to use the gradient vector evaluated at the point as our direction vector v that we used before. So this normal line to a surface at a point is denoted by the r vector sub n, and that sub n is what tells us it's the normal line to a surface. And so it's just going to be an r naught, where r naught is a point on the surface, plus t, don't forget the plus t in there, times a vector v, where the vector v is made of the first partials evaluated at the point. All right, let's do an example. In our example, we need to find equations of the tangent plane and the normal line to the given surface at the given point, okay? And our function is x plus y plus z is equal to e to the xyz, and the point is 0, 0, 1, okay? So let's go through all the steps. First step, we are going to define big F of x, y, z. And the way we do that is we move everything to one side of the equal sign. I'm going to write this as x plus y plus z minus e to the xyz. This is equal to 0. Okay. The second thing we need to do is we need to calculate the gradient of f. Okay, so we're going to run through and take partial derivatives. The first partial with respect to x is just going to be 1 plus 0 minus e to the xyz. The derivative of xyz with respect to x is going to be yz. And then that's our first partial with respect to x. The partial with respect to y will be 0 plus 1 plus 0 minus e to the xyz times the derivative of xyz with respect to y, which will just give us xz, comma. Now the first partial with respect to z gives us 0 plus 1 minus e to the xyz times the derivative of xyz with respect to z, which gives us xy. I'm going to simplify this so it looks a little bit better. So this is just 1 minus yz e to the xyz, comma, 1 minus xz e to the xyz, and then 1 minus xy e to the xyz. Okay. Now, third, I need to evaluate this at the point. So I need del of big F at 0, 0, 1. So everywhere there's an x or a y, put in 0. And everywhere there's a z, put in 1. And what's going to happen is I get 1 minus 0, 1 minus 0, 1 minus 0. So my vector, my gradient vector is just 1, 1, 1. That's it. That wasn't bad. Okay, so now we can get our tangent plane and our normal line. Tangent plane first. We have everything we need. For the normal vector, it's going to be the gradient of f of 0, 0, 1. And for the point r naught, we have 0, 0, 1. Okay. So the equation of a plane says we take the dot product of del f of 0, 0, 1 with r minus r naught and set that equal to 0. That's our good old-fashioned formula from before. So the gradient vector is 1, 1, 1. And the r minus r naught is a vector with components x minus 0, y minus 0, z minus 1. This is all equal to 0. I go ahead and do my dot product by multiplying the like components and adding everything. And I get x plus y plus z minus 1 is equal to 0. And that's it. That's my tangent plane. The normal line. With the normal line, I need, so this is r sub n, and it will be equal to r naught plus t times the v vector, where v is equal to the gradient of f at 0, 0, 1. Okay, so I go ahead and I pop those things in. It's the same r naught that we had for the plane. So r sub n will equal r naught, which is 0, 0, 1, plus t times v, where v is the gradient vector and it has components 1, 1, 1. We go ahead and combine these, and this will equal t, t, and t plus 1. That's our normal line, the vector form of our normal line. That's it. Okay. So those are a couple of the things that we can do with the gradient vector. We should look at an application as well. So for our application, we've got this problem here where we're told, suppose you are climbing a hill whose shape is given by the equation z equals 1000 minus 0.005x squared minus 0.01y squared. This shape right here, z equals, like before we do anything else, 1000 minus 0.005x squared minus 0.01y squared. This is an upside down It's a paraboloid. It looks like it is not a circular paraboloid. It is an elliptic paraboloid. Okay, and x, y, and z are measured in meters, and we are standing at a point with coordinates 60, 40, 966. I'm going to graph this, this hill. So since it's upside down, I know that 1000 is the highest point on the hill. So I'll just draw myself a hill. It's the easiest way to do this is draw the paraboloid first. Don't worry about being accurate. Just get a shape on here. Highest point is 1000. Okay, so they're telling us that we're standing at a point and the coordinates are 60 in the x direction, 40 in the y direction, and 966 in the z direction. So we're on the first octant, and let's get a point. So we'll be on the side. This is weird how we do this. So I know that I'm in the first octant. I go out pretty far in x, not as far in y, and I go up 966, so it's almost to the top. I'm about right here. But when I just plot that point in that way, you can't tell where that is. So what I'm going to do is draw a level curve so that we can kind of see that a little bit better. That must be in the first octant. Okay, it's kind of the best I can do. Maybe you can do better. Now, let's see. They're telling us that the positive x-axis points east. The positive y-axis points north. So that tells me that the negative x-axis is pointing west. And the negative y-axis is pointing south. All right, so that's our setup right here. And this picture is like worth $1 million right now because I can actually answer parts A and B without doing the work, but I can't tell you the rate. So the questions are asking whether we're going to ascend. Ascend means go up, or descend, which means go down. Okay, so the question is, if you walk due south, so due south would be heading towards the negative y-axis on the paraboloid. Not going around the paraboloid, but just like start walking due south, okay? In order to head due south, it looks like we would have to, let me get a different color here. We would have to, what's the best way for me to draw this? So we'd have to kind of go up and head towards the back, towards the negative y-axis. It's kind of hard to draw arrows in 3D. So my guess is that we would be ascending. I don't know the rate, but I know we'd be ascending. Part B is saying you walk northwest. Okay, northwest is pointing, let's see, in the second octant. So northwest is, it looks like about maybe in this direction here. Okay, again, hard to draw. But it looks like I'd be heading down. It looks like I would be descending in the northwest direction. So those are my guesses. Okay, so just visually looking at these, that's what I'm thinking. Okay, now they're asking us for rates. They're asking us about ascending and descending. So you should be thinking about directional derivatives. We have to calculate what are the rates of change. Okay, so first things first, before we write A, B, C, or D, we need to calculate the del operator on Z. Okay, so we're looking at del Z, and that means we need the vector with components of Z sub X and Z sub Y, which aren't too hard to calculate. That's nice. Z sub X, only the middle term gives us anything. Okay, and when I use the power rule on that, I get negative 0.01x. And then Z sub Y, only the third term gives me anything. And when I use the power rule on that, I get a negative 0.02y. Okay, that's my gradient vector. And I would like to calculate my gradient vector at the point that we're standing on. And that point is the 60, 40, 966. So I'm going to calculate my gradient vector of z of 60, 40, 966. Now, obviously, there's no z in my gradient vector, but I'm still, like, that's part of my problem. It's still there. It's one of my points. Okay, one of the parts of my points. So I'm going to put in 60 for x and 40 for y, and we get negative 0.01 times 60. And then we have negative 0.02 times 40. These work out to give me negative 0.6 and negative 0.8. If we wanted to see this in fractional form, this is a negative 3/5 and a negative 4/5. Okay, that is my gradient vector. And remember how the gradient vector is supposed to give us the direction of steepest ascent, right? The maximum rate of change that we could find. I have both a negative x and a negative y, so that would be pointing in the southwest direction. And if we look at our hill here, that kind of makes sense. We'd have to go straight up the hill if we wanted to do that. But I digress. So let's get back to our problem here. We have our gradient vector, and now I want to look at part A. Due south. I need a unit vector. And this is where stuff gets weird, okay? So if we're headed due south and we need a unit vector, well, due south has a unit vector of u equals, well, there's no movement in the x direction if we're headed due south, so that would be 0. And in the y direction, we're headed due south. That means going -1 on the y-axis. So a unit vector of 0, -1 would be a great representation for moving south. Okay? It's not made up. It's just taking advantage of the fact that we are going to be traveling along one of the axes. So we may as well use a unit vector that would represent the axes. So u equals 0, -1 is my unit vector for due south. Now, the directional derivative in the direction of u of z of 60, 40, 966 is going to equal the dot product of del z and u. So that's going to give me the dot product of negative 3/5 and negative 4/5 dotted with 0, -1. And when I dot that, I just get back 4/5. Okay, that is a positive value. So because du of z is equal to 4/5 is positive, we will ascend. Okay, because the question was, will you start to ascend or descend? We will start to ascend. We'll be going uphill. And at what rate? The rate will be 4/5, right, at a rate of, or we could write it as 0.8, but it'll be, we'll write it as 4/5 equals 0.8. And this is, it's kind of weird how we read 0.8, but it's equal to 0.8 meters over 1 meter, which means that for, like, we go up 0.8 meters for every horizontal 1 meter. So our rate is unitless, right? Because it's 0.8 meters over 1 meter. So it's just 0.8, that's it. But it's positive, we will ascend. Let's look at the next one, B. In B, they're asking us, if you walk northwest, will you start to ascend or descend? and at what rate. I already made a guess that we're going to descend, but now let's go ahead and calculate it. If we're walking northwest, we need a direction vector, and it needs to be a unit vector. So northwest has an angle of theta equals 3 pi over 4 from the positive x-axis. So u is equal to the vector with components cosine of 3 pi over 4 and sine of 3 pi over 4. And I know it's 3 pi over 4 because northwest is halfway through the second octant. Okay, so I can calculate these. My cosine will be negative root 2 over 2, and my sine of 3 pi over 4 will be positive root 2 over 2. That's my direction. Okay, so my directional derivative in the direction of this u of z of 60, 40, 966 will equal the gradient vector, negative 3/5 with negative 4/5, dotted with this unit vector I have here, root 2 over 2. It's negative root 2 over 2 and positive root 2 over 2. So do the dot product, I get 3 root 2 over 10 minus 4 root 2 over 10. And that is going to give me a total of a negative root 2 over 10, which is approximately negative 0.14. Okay, so it's a negative value, so we are descending at a rate of about negative 0.14 vertical meters for every 1 meter. Okay, and that answers part B. All right, part C is interesting. So part C says, in which direction is the slope the largest? Okay, well, we can calculate that. We know what maximums are here. The direction of largest slope is just the directional derivative. And then what is the rate of ascent in that direction? Okay, well, we also know that. That's just going to be the magnitude of the gradient. And then the last one is the weird one. At what angle above the horizontal does the path in that direction begin? Okay, so let's figure this out. Part C. I just need a little bit of room here. So I'm going to cheat and give myself a little bit of room by making things a little bit smaller. Okay. Last part, part C. We want the direction of largest slope. And we know that this is equal to the gradient vector, the gradient of z at the point 60, 40, 966. And we already calculated that, and we found it to be the negative 3/5 with negative 4/5. That's our direction of steepest ascent. And then the next part is the rate of the ascent, of the max ascent, is the magnitude of the gradient of z of 60, 40, 966. And that will equal the square root of the sum of squares, so 9 over 25 plus 16 over 25. And that will equal the square root of 25 over the 25, which is 1. And that 1 can be written as 1 meter vertical over 1 meter horizontal. if we want to kind of understand what the rate is meaning there. Okay. All right. The last thing that's being asked is, at what angle above the horizontal does the path in that direction begin? Okay, let's look at a little picture here. Here's P, our point, and the direction of steepest descent we found is -3/5 with -4/5. So we're heading kind of back like this. And we have a 1 meter vertical change to get there and a 1 meter horizontal change. Okay, that's our rate. And so if we were to put theta from the point, and like we've got our horizontal line and our vertical line, so that really gives us a nice right triangle right there. And then we can look at, well, tangent of theta is going to equal 1/1, which is just 1. And so theta will be the arctan of 1, which is pi/4. So the angle that the direction of the largest slope makes with a horizontal line is pi/4. That's it. Okay. So there's a lot going on in this problem. Definitely take some time going through it. You've got my video to watch, but you can also maybe pause me at some points, try working it on your own after you've watched me go through it. And then, if you have questions, please just reach out. I'm available.